In this lecture, we will study D, E and P relation. In the reference to electrostatics, D is displacement electric field, E is the applied field, and P is the polarization. As far as free electrons are concerned, only electric field is there. But in the presence of bound electrons, there exists displacement electric field and so polarization and this relation. In this lecture we will discuss how it can be obtained and significance. The presentation and the lecture will be like this. First, we will introduce electric field, displacement field and polarization. The significance of each will be discussed. These all are vector quantities. So we will discuss from where these quantities will originate and what is the relation, expression, how to get the relation between this we will discuss on the basis of Gauss law, and finally we will discuss limitation of this. Using this lecture, student will learn about the existence of relation D is equal to epsilon 0 E plus P. P is polarization and D is displacement field. This relation has significance in dielectrics, in presence of dielectrics. As we know, the dielectrics means two electric behavior, and this is possible in insulating materials which are not having any free electrons, and it gives a kind of displacement due to electric field. We will discuss these in detail. What is electric field? This is a very basic question. We have discussed in this lecture a lot about electrostatic charges. Charges are there, charges surrounds us. Whenever we have electrostatic charges, these charges creates a force in the surrounding environment. And whenever we want to go, or another charge want to go towards the charge or away from the charge, there exist some forces of attraction or repulsion. These forces form an environment, then environment is called electric field. Electric field due to single charge, then due to dipoles, then due to multipoles. We have discussed in previous lectures. This can be taken from there. But as far as only electrons are concerned, electric field can be calculated by either Gauss law or Coulomb's law. When we have moving electric charges, then this will also give current or time varying fields. However, the situation is entirely different in dielectrics. I think all are aware of this word dielectrics. This dielectrics means two electric charges. The two electric charges are positive charge and negative charge. We termed it dielectric due to its behavior, due to separation of two charges. However, we also have another name for these materials called insulators or bad conductors in the normal words. Insulating materials are those materials which are not having any free electron. Insulating materials are those materials which cannot conduct electricity. Whenever we use such materials in electric fields, they can't allow current to pass. That we knew this for many years. But the interesting thing is, suppose you apply electric field and the electric field will not be allowed by those materials, then what happens? As a matter of fact, whenever we apply field, of course they can't allow electric current to pass, but they accommodate that field in the way that they displaced from their equilibrium positions. That is called, the polarization is called dielectric polarization. Normally, many examples may be given, but normally you can say in any atom, you can say this is the center of positive charge. Of course, this drawing is not good, but it's just almost spherical in shape. I want to draw here. So I am trying to explain you by this circle that the electron, suppose this is the circular shape, a spherical shape, and electrons lives here. So if electrons are layered uniformly about the center, then the center of negative charge and center of the positive charge both are at the center here. And so whenever if you are not applying any electric field, then this will be the value. This is for E is equal to 0. But when you apply a finite field here, then in presence of this field, this take a spherical shape. The Why this happens? Because in the presence of electric field, the electron move to this towards positive side, and so there exists a charge separation. Now the center of positive charge and center of negative charge will not coincide each other, and the center of negative charge will be moved towards left if the field direction is like this. This is called separation of charges, and this call is called polarization or dielectric polarization. The same is also shown here. If you are also having some dipoles as shown in the figure on the right hand side, then these in the right hand side, these dipoles are shown in random motion. In our figure, I have explained in terms of electronic polarization. But this type of polarization, when these dipoles already exist, called dipole polarization, we have discussed this in a separate lecture. So, in presence of electric field, they arrange here in a very specific manner, you can say, and here it is random. So, this is another kind of polarization, dipole polarization. But overall, there exists a separation. Do we know why it happens? It happens due to bound charges. So now we must know the meaning of these two, free charges and bound charges. Free charges, those charges which are free to accommodate electric field, but bound charges are not free. They accommodate by displacement. Free charges, bound charges are likely to move through an object to create moving electric charge or current, while free charges move there about easier and can more easily move their electrons through a material. So, in the case of bound charges, as we are having in the dielectrics, the displacement occurs, and the displacement occurs that give birth to displacement current. Now, in presence of dielectrics, there exists a new concept, the concept of displacement field that we have shown in the previous slides. A vector field that appears in Maxwell equation. It accounts for the effect of free and bound charge. As a matter of fact, we have developed this to account these two charges, free and bound. From the name, this stands for displacement field vector, as in the related concept of displacement current. In free space, the electric displacement field is equivalent to flux density, a concept that lends outstanding to Gauss law. In the intersystem of units, it is expressed in unit of Coulomb per meter square. Or Q upon A, we generally termed as. So it is something that is developed due to bound charges, that is developed due to dielectrics. In Maxwell equation, in free space, there is no need of this. But when we talk about Maxwell equations in some mediums, then this is generated. Explain. In a dielectric material, the presence of an electric field causes the bound charges in material. And these bound charges means atomically clear and their electrons slightly separate due to this. This is introduced here a local dipole moment. And this local dipole moment is represented by electric displacement. Yes, so you can say the field value applying outside, but this is local dipole moment exists here. Another term which is a byproduct of this relation is polarization. As we have discussed, then due to field, a bound charge is displaced and form a local dipole displacement field. This is also represented as polarization. Separate the total volume charge density into free and bound charges, and the density can be written as function of polarization P. This polarization is defined to be a vector field whose divergence yields the density of bound charges. The density of rho B. The polarization arises on the plate's surface of the dielectric materials. If we consider a dielectric material placed in an external field E0, for example, we are assuming here the initial field is E0 between the plates of capacitor. Now, due to external field, there will be a shifting of center of gravity of positive and negative charges. We have discussed this in previous lectures slides also. The positive charge are displaced in the direction of applied field, whereas the negative charge displaced in the direction opposite to applied field. Therefore, the positive charge is induced on one surface while negative charge on other. The phenomenon of appearance of the charge on the surface of dielectric induced by external field is called dielectric polarization. The charge on the plate of the capacitor is called free charge, and charge induced on the surface is called bound charge. When the atoms are placed in electric field, they acquire induced dipole moment and in the direction of the field. This process is called polarization, and atoms are said to be polarized. The induced moment, dipole moment, is proportional to applied electric field E, and P is proportional to capital E, so P is equal to alpha E. This is something about capital P. We have discussed D, we have discussed P, and now we will discuss the relation. Here, these all D, E, and P shown. We have defined all this in the previous slides. The electric field that we have applied is shown, these lines are shown in the center. Due to this electric field, as the green lines are showing here, the parallel plates between which we are applying applied field, and on these plates the charge is here we have shown sigma and minus sigma r. Now since we are applying and keeping a dielectric substance which is shown in the center here, dielectric substance as we have discussed that has bound charges, and due to this there exists a separation of charge, and due to this separation charge the field is known as displacement electric field, and these are called dipoles. Dipole gives us polarization. So we have three vectors here, D, E, and P. D lines are shown on the right hand side. As we have introduced these three words, D, E, and P, E is the applied field, E is the polarization, and D is the displacement field. And displacement field is due to these two, electric field and polarization. Then this relation is between these vectors. D is equal to epsilon 0 E plus P, where epsilon 0 is the permittivity. Now we will derive this, we will get this relation in the next slides. Now we will obtain the relation between polarization vector P, displacement D, and electric field E. Of course, the relation is D is equal to epsilon 0 E plus P. But we want to get this relation using Gauss law. We assume that we are applying electric field, and this electric field we are applying on two parallel plates, and then we keep these a dielectric material between these plates. In this expression we are assuming two parallel plates, and in this electric field is there. We are assuming this electric field as E0. Then we will keep a dielectric substance between these two plates. If we keep this dielectric plate here, substance here, as we know, the first plate will be, I am showing here, positive charge, and you can extend this positive charge all over here, because this end on the second plate we will have negative charge there, since we are applying the. But whenever we put this dielectric, the induced charge will be there, and the induced charge will be like this, minus on this charge and plus on the opposite, like this. And there is a dielectric constant also. Here I have shown a plate on, and we applied positive charge. Obviously, if the field is in this direction, then this opposite field will be negative. Opposite plate will be negative. We have assumed the area of plate is A and the field is, yes, E0. If we take first plate as Gaussian surface, as it is shown here, this we have assumed this as a Gaussian surface, first plate. As we know, then we can use the Gaussian law, Gauss law, to calculate electric field, and we have chosen the Gaussian surface in such a way it enclose only this plate of area A. Then according to Gauss law, we know this, the flux enclosed by this surface is equal to Q over epsilon 0. So we will obtain this relation using this. Since we have taken only first plate, then the applied field is E0, so this is our electric field. E0A should be equal to Q over epsilon 0. From here, we can write the value of electric field. Q is equal to epsilon 0A. This is your Gaussian surface. Now, if we place a dielectric material in this, and we now in remember this here, I have taken Gaussian surface in the special manner, so that the Gaussian surface includes not only the surface of this plate, metal plate, but also the surface of dielectric material. So now you have, if you want to calculate the charge inside this surface, then it is the Q that is always there, but induced charge is also there, Q prime. So the effective charge will be Q minus Q prime, and this will give you the electric field. That electric field now is called E. I am assuming the dielectric constant K here. In this case, you can write this law as E into A, Q minus Q prime over A is epsilon 0. So from here, you can calculate the electric field. We also know this, that the electric field is now become 1 upon K times the E0. So from where we can also calculate this electric field. Q prime is the induced charge on the surface of the electric fields. And we know that the Q prime is always less than Q, because indeed is an induced charge. Now we will equate this electric field to electric field that can be obtained by Gaussian Coulomb principle, that if the field is E0, and if we place the dielectric constant K, then field will become E0 by K. So we have two relations and we will equate it. We also know from the Coulomb's law that E is equal to K epsilon 0 A, because the field become 1 upon K. Now we have two relations, one from this Coulomb's law is to K epsilon 0 and second one from Gauss. We can equate this and get the results. Yes, if we equate this, Q is equal to K epsilon 0 A is equal to Q upon epsilon 0 A minus Q prime upon epsilon 0 A. And this can be taken out here and this will result here in this way. So this will be plus here. Now this portion Q upon A can be written here and epsilon 0 can be passed here. Now this Q upon K epsilon 0 A, we know this is called E. This is called E and this is termed as D. We will get the relation in the next line. Q upon A is defined as displacement field which occurs due to displacement of bound charges. P is polarization vector and the relation is D is equal to epsilon 0 A plus D. We can also obtain one relation, electric field density. That we know the delay D is equal to epsilon E. And epsilon can be done as epsilon 0, epsilon R. So if we place this here in place of D, then according to D's relation, epsilon 0, epsilon R E is equal to epsilon 0 E plus E. If we substitute this relation as epsilon R minus 1 is equal to xi, then a new relation exists come here, that is P is equal to epsilon E plus epsilon minus 1. That is called polarization. So there is another relation between polarizability and susceptibility. So thank you. In this lecture, we studied the relation between D, E and P and the relation between polarization and susceptibility. These equations plays an important role in dielectric substance where bound charges exist. Thank you.